Welcome to my presentation on visualizing hypothesis testing. My name is Ayodele Ojo and I'll be taking you through a 14-page slide pack. Hope you have an interesting presentation. We have an agenda. The agenda will cover what is an hypothesis, types of hypothesis, bell curves and p-values, null and alternate hypothesis, an example of each, important takeaways, which will cover key points, 4 in total of this presentation, an opportunity for you to ask questions, and an opportunity for me to give you thanks. There's a reference page for this slide pack, which will reference topics or academic journals that I've referenced in putting together this slide pack for your benefit. Very simply and quickly, the question is, what is an hypothesis? An hypothesis is defined by Sekaran as a tentative yet testable statement which predicts what you would expect to find in your empirical data. Essentially, you have 4 types of hypotheses. You're looking at what you call the null hypothesis, alternate hypothesis, directional hypothesis, and non-directional hypothesis. They are all taken from the same book. The page has been referenced. I'll give you a few seconds to go through that, and then we'll move on. Bear in mind that we'll be focused on the top 2 ones, which are the null and alternate hypothesis. Before we go into the examples of null and alternate hypothesis, there are 2 things we need to talk about. We need to talk about the bell curve. Now, the bell curve, typically called a normal distribution, is this red base here, which looks like a pyramid, but it's not a pyramid. And essentially, it has 5 parts. So roughly this bit that way, this bit here, this bit here, this bit here, and this bit here. When looking at a bell curve with the 5 parts, they typically, on average, most of your occurrence for your population, for your sample, will be found here. Then there will be a few outliers here. So if, for example, we're looking at the average age in a class of 30, what this bell curve will be telling us is that roughly, given that you'll be looking at a class, a lot of your pupils will be within this area here. Then there will be a few people potentially that will be older than the average, and you'll find them here. And there will be some people slightly younger than your average, and you'll find them here. And then there will be a few more outliners who will be extremely old, which typically will be maybe 1 person or more, and a very young person. So basically, it talks about the distribution of the population in your sample set. Before we move on, we need to talk about p-values. Now, p-values as defined here basically shows the probability of obtaining an effect at least as extreme as the one in your sample set. Basically, what we're talking about here when we talk about p-values is the fact that we are saying, based on the p-values you obtain from your population or from your sample, the likelihood that the result you have received is based on a randomized fact. Again, you have your bell curve, which contains your observed data, as you see here. Now we have these sections are called the p-values, which you get from your population size. We have probability increasing upwards. What is missing here is what you will call your significant level. Now, your significant level has to be on both sides of the bell curve. So I'm going to put in some lines here, basically dissecting the curve into 2, with an assumption that here we've got the positive side and here we have a negative side. Having a positive side or negative side is not necessary. You can have everything on the positive side or some of the negative side, but just for ease of understanding. And then we have a missing line here, which we call the significant line, the significant level. The significant level is typically called alpha. And out there are various significant levels that can be used, but on average, the most commonly used ones are 0.05 and 0.01. And here what we're saying is at 0.01, we're saying that the likelihood of getting the same set of data due to the same set of results due to randomness is 1%. If we're using a significant value of 0.01. Alternatively, when we are saying it's 0.05, we're saying that the likelihood of you getting the same result is equal to 5 or less than 5%. Now, one thing to bear in mind here is that when using the p-values, a key point is that you write up your hypothesis, which is what you're trying to test or what you're trying to prove in the null. In the null hypothesis, if you remember, our null hypothesis talks about relationship between two variables, where we are saying in essence that there is no relationship. So in an example where we've said there is no relationship between speed and distance covered over time, we know there is, but if we say that there isn't, we need to write it up as a null, as stated, which means that when we get our data and we have a p-value of less than 0.05 p-value, it means that we can reject the null hypothesis and accept the alternate hypothesis. And this is where we talk about the visualization of hypothesis. Talking about it makes it a bit difficult, but by visualizing it, it will make it a bit easier. And on that basis, we have 4 examples that will bring this point home. Example 1, called visualization 1. We have your normal distribution, and as you can see, we have your negative side here in this example and your positive side here in this example. This is basically your normal distribution, and it's split right in the middle. The research question here goes thus: on average, are widgets from Akai widget company defect free? A quick look at the diagram shows that at the middle it is 0. So it means on average you get 0 defects. And when we're talking about average, we're talking about the mean. The interesting point to note is that this point here also typically represents the mode, which is the highest repeated frequency, and at the same time, typically in a normal distributed bell curve, represents the median, which is the middle of the distribution. Now, to state a null hypothesis here, we are saying that at the average point, there is no defect. And we've written that out as a null here, which is on average, widgets from Akai widget company are not defect free. We've written it this way because when we write our null hypothesis, remember what I said earlier on, we have to write it in such a way that we're saying there is no relationship, so that when we put in a p-value of say 0.04 and we have our significant figure alpha of say 0.05, we are in essence saying that because our p-value is 0.04 for our sample size, for us to be able to reject this null value, our 0.05 is less than the significant level. This allows us to reject the null value and then on the counter accept the alternative hypothesis. Now the alternative hypothesis says on average widgets from ICANN widget company are defect free. Note, we know for a fact that looking at the diagram here, on average at this point here, ICANN company are widget free. We've already known that from the result. So writing a null hypothesis is quite easy from this point, because basically we need to write a null hypothesis that will be rejected once we get a value wherein our p-value is equal to or less than 0.05. We'll use another example. And here we're comparing two groups. Group 1 in blue is a league group, which we should say is adult, and the group in red is the minors. Now, on the y-axis, we have the number of home runs increasing, and on the x-axis, we're talking of the fraction of the numbers of people that can actually hit home runs. Now, the research question goes thus: does the average minor league have more home runs hitters than its corresponding minor league team? Does the average major league, so blue is the major league, let's make that clear right here, have more home run hitters than its corresponding minor league? Again, a quick look at the two bell curves shows us that for the major league, you're looking at number of, on average they have 16, whereas for the minor league it is just a bit, it's definitely under 16, probably 15. So let's just assume that it is 15 for the minor league. And the second question is that does the average major league team have more home runs hitters than its corresponding minor league? Here, looking at the two bell curves, we know that that is not true. Actually, for the major league, on average, it is higher than the minor league, which is 15. As such, our null hypothesis must be written in such a way that we can reject it and the alternate hypothesis confirming what we observed there, that the average of the major league is higher than the average of the minor league, which means there is a difference between the two. And we have done that here by writing this null hypothesis, by stating that the average major league team do not have more home run hitters than its corresponding minor league team. The alternative hypothesis to that is that the average major league team have more home run hitters than its corresponding minor league team. Looking at the diagram, you'll see that the alternative hypothesis is correct. However, on the basis of null hypothesis and alternative hypothesis, we have to write a null hypothesis, which is what we will test our p-values against. Once we reject the null hypothesis, then we're saying actually the alternative hypothesis is the case. Let's go through one more example. However, before we go to the next example, I just need to talk a bit more about bell curves and standard deviation. Standard deviation, as explained here, fundamentally shows how closely or how widely data is spread. So the wider the data is spread, the broader the bell curve, and the closer together the data is, the steeper the bell curve. Essentially, this bell curve was obtained by research into the incomes made by CEOs in different industries. Now, looking at these two bell curves, two things comes into the mind. It's saying here that essentially for professional societies where you have CEOs can make between just a bit under $500,000 and just a bit above $500,000. So you're looking at 454,276. But if you go to the other bell curve, which is a bit broader and is looking at trade groups, what we're seeing here is that in this scenario, CEOs actually make between just under $500,000 to above $1 million, which is a wider range, simply saying that 500k minus 1 million minus 500k means there is a 500k range in here, whereas here you have probably 50k range, which is why this is a very steep curve when compared to this, which is a broader curve. The rule of thumb here is obviously that the flatter the curve, the higher the variation, which means you have a wider range of people falling to that average mean set. So let's go. So here we come to our third example. Given the bell curves we've used in the past, we can see that we have a steeper bell curve and a wider bell curve. With the bell curves, we're looking at a population of about 100 for the blue one and a population of about 60 for the red one. Basically, the numbers here representing the number of people served per hour. And we're looking at the efficiencies. Now, the research question states here the efficiency curves of the red and blues were recorded. Do the teams have equal mean efficiencies? When we talk about mean, we're talking about the average. Now, the average here for the blue is 50. The average here for the red, don't forget it is between 60 and 0, is 30, right in the middle. So we know, looking at the picture there, that in response to this answer, the teams do not have equal mean efficiencies. Now, to write a null hypothesis, we have to write a null hypothesis that basically will be rejected so that the alternative hypothesis will be accepted. Now, the alternative hypothesis that will be accepted will be the one that shows the relationship between the red and the blue teams. So the first thing is to try and write the null hypothesis. And we can think, just looking at this, we can say the null hypothesis will be teams blue and red have equal mean efficiency. But we know that that is not the case. So we put this down as our null hypothesis. And this will be our, shall we say, HA, our alternate hypothesis, while this is H0, which is equal to a null hypothesis. So if we revisit this topic again now, this conversation again, we say teams blue and red have equal mean efficiencies. We know that's not the case. And we know that if it is tested, we have 30 for team red and 50 for team blue. And on that basis, the hypothesis that will be correct would be the alternate one, which is teams blue and red do not have equal mean efficiencies. Now, obviously, the ability to reject the null hypothesis will be based on what your significant level alpha is and in comparison to your p-values. Okay, so if we're using a significant level of 0.05 and we have a p-value less than 0.05, it would mean that our null hypothesis will be rejected and we would accept our alternative hypothesis, basically saying teams blue and red do not have equal mean efficiencies. So here we're talking about a fourth example where we're using scatter diagrams, and this one talks about correlational tests. So I'll quickly read through this. A German study tested how larger industrial use vans utilize gasoline. One of the analyses plotted miles per gallon (mpg) versus the weight of the various vans in the study. After plotting the data on a scatter plot, the researchers performed a correlational test and found a significant correlation. However, they forgot to state the hypothesis test in their published paper. Question: what are the study's null and alternative hypotheses? In this scenario, we already have the results. So we are basically just simply working backwards. We see a line graph right about here. And that line shows basically divides the scatter plots relatively equally above and below that line. We know from theory, from physics, that the heavier the van, the more fuel is used. So there is a direct relationship. The line graph there, the scatter diagram there, shows that there is a direct relationship. You can see it's going up to down. So the bigger the vessels, the less miles covered. So to state a null hypothesis here, we need to say an hypothesis wherein the null one will be rejected and the alternative hypothesis will be accepted. In this scenario, we know there's a relationship and we want that to be the acceptable one. So the null hypothesis for that will be there is no direct relationship between the volume of gasoline consumed and the weight of the van. And the alternative hypothesis for that is that there is a direct relationship between the volume of gasoline consumed and the weight of the van. Basically, by stating the null hypothesis using tests like p-values, which in this case is less than 0.0001, or correlational value, which is in this case is equals to minus 0.87, we can reject the null hypothesis, which states that there is no direct relationship, and in so doing accept the alternative hypothesis. The important takeaway of this visualization of hypothesis theories is very simple. Creating hypothesis tests, hypothesis is about relationships between variables. Now, the variables may be two or it may be more. If you remember our examples where we looked at various themes, and we looked at the last piece about correlational relationship. These variables need to be expressed in a form that is in the form of a testable statement, and that is why we have the null and alternate hypothesis. Basically, when stating an hypothesis for testing, it should be in the four examples we've given, which is either directional, non-directional, null, and alternate hypothesis. The other bit there is the visualization. Point one there is that we say different shapes and types of visuals can be used to depict a null hypothesis. So we've looked at bell curves, we looked at a very steep bell curve, a broad-based bell curve, which between the two of them have different standard deviations. We've also looked at line diagrams and line graphs using correlation to determine how we want to state a null hypothesis, and there are other diagrams out there that can be used to state what a null hypothesis is. The other thing there is that we can quickly show what type of relationship exists between the variables. So here we're saying that simply by looking at the diagrams we have in examples 1, 2, 3, 4, we could easily tell how to write up or how to come with a null hypothesis and our alternative hypothesis. So the visualization makes it easier to actually write up the hypothesis that needs to be tested. So at this point, I'll have to thank you for watching. If you have any questions, please put it on the academic page of the class, and I'll be happy to respond. At the end of the day, have a great day. The next final slide, which I will show after this, will be the references of some of the materials used during the course of this presentation. Thank you for your time and have a great week ahead. Thank you.